Be talking about using the IPython Notebook with IPython Cluster for reproducibility and portability of atomistic simulations.
Thank you. Yes, I'm Zachary Trautt, and I come from computational material science, specifically atomistic simulations. And I'm going to show you what that is. And originally, I thought I was going to be coming here to talk about reproducibility, but in reality, I'll probably be talking more about workflow and automation, simply because I felt that those things were the greatest impediment to make my work reproducible. And I'm going to show you why. I thought that would show you the challenge that I face with that. Another thing to note is I only recently adopted or started adding Python to my daily activities. So in a few short months, I went from doing hello world with Python to completely automating everything that I do. A quick outline of where I'm going to go. I'm going to quickly show you an introduction to my work, sort of impress why I think workflow is necessary for me to do my job better, and how I use IPython Notebook and IPython Cluster. And I'm certainly impressionable, so if any of you think that I could be doing something better, that's part of my reason for coming here. So very quickly, here's a movie showing what I do. And I really care about the relationship between structure and properties and material. Like, for example, the metal in your car is polycrystalline. And what that means is there are different regions in that metal of perfect crystallinity, and then they have different orientations. And the planar defect between them is called the grain boundary. And grain boundaries are pretty important in that they're a strengthening mechanism for the metal in your car, for example. And I am interested in studying the origin of those structures, of that microscopic structure when we process a material, like bang on it really hard, heat it up, so on and so forth. So I set up this simulation, and what you're seeing here is several thousand atoms, which is actually a very small atomistic simulation. I chose it just because it makes a good movie. And you see two grains, and between them is the grain boundary, and I'm watching that grain boundary move. So to create this study, or to do this study, I first had to create an initial configuration. And I don't get it right on the first try. I have to do several thousand simulations and pick the one with the lowest energy. And then from there, I do the production run. And just doing one simulation like this isn't enough, so I do many, many thousands more of those. And in doing that, I sample a lot of different software to paste it all together, including the software I use to do the visualization to color those atoms. Because I want to identify certain defects. So I just wanted to impress just the complexity of my problem. I have many parameters that I might care about, and many of the problems I focus on require a very, very large simulation domain, meaning that any individual task is itself parallel. So whatever solution I use must address the fact that I need to distribute parallel tasks. The pictures on the right are a slightly simpler atomistic problem. It's called, I wanted to measure what's called the stacking fault energy. So the figure you see on the top is a perfect crystal, and we cut it in half and displace the upper half in 2 dimensions and watch how the energy changes. And the figure below was generated by matplotlib in a IPython notebook that I'd like to scroll through at the end if time allows. And that figure on the bottom, every single pixel represents an individual atomistic simulation, of which there were more than 10,000. So how did I used to do things? Well, I did a lot of bash scripting. So however many parameters I wanted to explore, I made a directory. And within that directory, I did my pre-processing, production, post-processing steps, and then gathered my data. If I simply wanted to make my work reproducible, some people might recommend just logging what I've done. And it's true, that probably would improve reproducibility. However, it doesn't take me out of the equation. So if I want to expand the parameters that I'm exploring, it really isn't scalable from my perspective. So, and the other question is, I would ask if I'm just logging the steps, have I logged the recipe of how those steps were were assembled. So this chart just shows what I want to do, and in general terms, what I think a logging tool could do if I was searching for one, and a workflow tool. I want to be able to automate and assemble all of my tasks. I would hope that it improves my reproducibility. I'd like it to be reusable as well, such that I can construct this workflow on a local machine and then run it on something like the Amazon cloud. And I'd like to make it a lot easier to build upon past work, because a lot of the studies that I've done, I sample a very, very small range of parameter space, meaning that it's potentially useful for somebody else if the barrier is low to do what I've done. So, getting started, I started searching around and accepting emails from many people, trying to figure out, well, what's the best way to paste together my workflow? And I asked 3 fundamental questions. The first of which, is it possible to distribute my parallel task? And I was surprised by how few examples that I found. A lot of the workflow tools that I downloaded and turned on, they work just fine on my laptop, but I kind of felt left out that I couldn't find a lot of examples for distributing parallel tasks. And the next question is, does it provide more benefit than cost? Because I think a lot of people, if it takes more work than benefit they're going to get out, they might not adopt it. I'm thinking beyond myself in that picture. And the final question is, am I going to have to reinvent the wheel to do very simple things? I think the last two, Python is really an obvious choice. The first one, maybe not so much, but after reading some of the documentation of IPython Parallel, I could actually see light at the end of the tunnel as compared to some alternatives or traditional tools. So the picture on the right is just the cartoon demonstration of what I wanted to do and what I was able to do with the IPython Notebook, or just IPython or standard Python in general. I liked working with the notebook simply because it was a nice, clean, intuitive interface that I could easily show someone else what I did. Recently, I passed off an IPython notebook that I had made to do a certain test to one of our visiting undergraduates at NIST, and he was able to make minor changes and measure the same property in a different material. So I really like that it's easy to use, that there's a lot of packages available, and I like that my workflow is encapsulated in a single file. I think for new people, digging through a library made up of many files can be somewhat cumbersome, and they can become easily distracted about what they're looking for. And I think this has improved the reproducibility of my workflow. There's a lot more things I want to do, but I thought this was the first step. So I'm going to take you through code that I pseudoized from an actual notebook to show you exactly what I did. And this is actually very, very similar to a lot of the documentation online. So I define all the steps of my workflow as a Python function, and then I assemble those functions within a global a simulation function, and then I simply run it. And in this example, I can run this workflow in serial, or I can map it to parallel resources, and I've highlighted those as such. And these are just the direct and load balance views to my IPython cluster. I need the direct view such that I can push the definition of the various subfunctions and the parallel decorator to actually execute them. And I'm going to talk about that in greater detail later on. So here's just a sample of some of the steps that I need to do for a simple simulation. One of them is to make a unique working directory, and I wouldn't be surprised if somewhere within Python that a function like this already exists. I couldn't find it, so I may have reinvented the wheel. I need to write an input script for my molecular dynamics code, which I'm using LAMMPS. And then I need to run it. And I've hard-coded in MPI run for your benefit. And I think some of you might be looking at that and thinking, wait a minute, what's going on here? that doesn't sit right. Well, I'm using IPython Cluster in a fundamentally different way than I think a purely Python researcher might do. So if you're trying to solve a fairly heavyweight problem in pure Python, you might use IPython Cluster in the way that I've shown on the left, where however many CPU cores that you have, you turn on that many IPython engines and run your simulation. Because I want to distribute parallel tasks, I have more than one processor per IPython engine. So if I want to scale up my work, I can simply add in more processors, which means more processors per IP engine as well as more IPython engines. So lastly, I wanted to do a better job about storing my data. Generally, a lot of people do it pretty sloppily, and I sort of converged on HDF5 with PyTables, but I faced a problem with that. In Googling, I did find a concurrency safe version, I think, but I didn't have it installed, and I wasn't sure if it was the default version. So I chose to address this problem on my own, and the way that I did that is I have an IPython engine whose duties are specific to saving the data, and all of my worker IPython engines can see that. So the first block of code in the top left, I launched the IPython client. I create my load balanced and direct view of my IPython engines, and the data storage engine is the first one, and then I have all the worker engines. They see that view as well. On the top right, I have a function that I've created for saving my data. And on the bottom left, that's where I actually use it. And this is the very last thing that I do within my simulation function. And I do an hview apply sync on that such that the synchronous application makes it such that each worker engine has to wait in line to record their data. For some people, that might cause a problem. For me, the level of computations is greater than the data store. So when I run this notebook, I typically see full utilization of the processors. So I just wanted to quickly jump to an example notebook. It's not live. I'm just going to scroll through it simply because I didn't want to connect to the cluster. So I have a few static parameters. This is just the paths to various things that I need, like the lamps executable, where I am on the remote file system. And in the spirit of easy reproducibility, rather than manually downloading the potential I use, and well, what's a potential? So the definition of forces between any pair of atoms is defined by a potential. So I download this potential directly from the repository, so the user doesn't have to do that, or somebody who wants to reproduce my work. Again, I configure the IPython cluster, and this is a direct copy and paste from what I showed you in the PowerPoint presentation. And you can see I'm having it spit out that I'm accessing 64 nodes. This workflow, I have run it with more than one processor per IPython engine, but because there are so few atoms, that actually slows it down. So the last time I ran this, I ran it with one processor per IPython engine. So I've created a very, very simple HDF5 table in some of my production notebooks. This takes up a significant portion of space. Here's my function again for making that unique working directory. This is my lamps input script function, and it's very, very literal. So somebody who needs to understand lamps can just easily read one of these lines and go look up the documentation. And then I execute lamps. Here's my function again for recording results, similar to the pseudocode. And here's my simulation function where I paste it all together, making my working directory, making that lamp script, running it, gathering the data with NumPy load text, and then recording the result. I need to prepare the input parameters for my workflow, and there's probably a better way to do this than my two nested for loops for creating these lists, but that's how I did it. New user. And I map this simulation to the available computational resources. And now I want to start plotting the results. Here's just a simple line trace of the two-dimensional parameter space that I was exploring. Matplotlib. Here is the 3D surface plot that I showed you at the beginning, and a contour plot. So in summary, I really liked how easy it was to start using Python, and how I was able to do a whole lot with very little effort. In the past, I faced a problem where I wanted to solve a specific question where I was going to generate more data than I had hard drive space for. So I used Bash to create a consumer producer model such that I was analyzing the data runtime and getting rid of it. And in retrospect, I probably could have done that a lot better using some of the tools I'm using now. And really, there's some grand challenges that we face in material science. And I see pictures like the one that I've recreated, drawn, where the goal is to try to start tying some of these things together because relevant behavior takes place at different length and time scales. And here's what I've tried to do to help assist that, is to make my workflow that I hope is reproducible and provide data that is self-descriptive. Thank you for your time. So I haven't crossed that bridge yet. I would really like to incorporate something like Sumatra in my work, but I would really like to be. Oh, I'm sorry. So the question had to do with version control, and there's a lot of layers to that, as Daniel mentioned in his talk, in that there's the version control of, in this sense, your workflow, the version control of all the software that you're using, and then all the times that you've used it. So I'm proceeding slowly with that question, and I would really like to use something like Sumatra, but I would like to use it in such a way that I'm using it for the global simulation function as well as all the tasks, and that it can somehow record the order in which various tasks were performed. So that's the next step. Thank you. Yes? That's a fantastic question. And the answer is I take it out of the loop. I'm effectively replacing the batch system.
Just to add to that, IPython does support PBS and several scheduling engines. So you can actually define a profile where when you start the cluster, it goes through the batch queuing system. And it's in the documentation. Yeah. Yes.
Then you have to have two fixes, one to start the thing and one to clean up the end.
It's similar. We can go into the details later. I don't want to.
Did I repeat the question?
No.
Okay. Well, so the question had to do with launching to the batch scheduler, and Fernando mentioned that some of these things are built into IPython, and that's actually what I used first, is the MPI execute of the cluster, and that actually didn't work because it sort of reserved, I don't know the specific, or it locked it up such that I could no longer use the MPI environment. So I needed to launch my IPython engines without MPI because I use MPI for my tasks. So that's an interesting question. Yes?
Do you have your short list? That was a tremendous list. Do you have that available as far as sort of the notes that you took along that list? That would be great.
It's an incomplete Excel spreadsheet.
Okay. Love to have it.
Well, it actually started out as a.
Sorry, can you repeat?
Oh, I'm sorry. So the question is I had that huge list of workflow tools, and the question is, can I take a look at that? And my answer is, sure. I'd be happy to email you the incomplete Excel spreadsheet. But that list started from. Somebody actually published a paper where they took a look at some of those workflow tools. And one of them looks really attractive to me. However, in order to use it, I still had to functionalize my code such that I can just start plugging in those functions. So Python to me was the first step simply because of the limitations I realized when I was doing this in Bash. Yes, I'll do that. What? So the question is, can I post the notebook? And the answer is, yeah, I will do that. I'm making sure that I jump through all the hoops to do it correctly as far as the fact that I'm working at a government institution.
What pain points did you find on the IPython APIs or documentation? It would be very useful for us to know what did not go well, what made your life more difficult than it needed.
Okay, I'd be happy to sit down with you, but really I've only noticed. The question is, what kind of difficulty have I faced in doing this? And really, the kind of things that I've noticed are very, very trivial things that I was able to overcome or just ignore, minor quirks. The only catastrophic thing that I had happen was, as I was running a production notebook that had been running for several days, and for whatever reason, the notebook itself crashed. But because I'm sending all of the work to the IPython cluster, it kept running, and my data was there the next time I turned the notebook on. And, well, it was there in my HDF5 file. Yes? So what he said was it would be a good idea if a lot of this was incorporated, and I agree. And it could be that it already is, and I just simply didn't have enough skill in Googling for the solution. Okay. Okay. Thank you for recommending looking into celery and Luigi. I had not heard of those, and they weren't in my short list. Yeah. Like the vegetable and the Mario player? Okay. Thank you.